Hello students, in this lecture we will discuss the behavior of prism, lens and the mirror. As you have seen, in the case of the prism, the ray of light always bends towards the base. The ray of light always bends towards the base of the prism. This behavior of the prism can be explained on the basis of wavefront. Let MB is an incident wavefront. And it is clear from this figure that the rays from the different points of the incident wavefront passes through the different thickness of the prism. The ray which travel through this portion will cover less distance as the speed of the light in prism decreases, and the waves from this portion of the wavefront in the same time cover more distance as it travels through the air. As you know, the wavefront is always perpendicular to the ray of light, so the shape of the emergent wavefront is this one, and we can say the rays bends towards the base of the prism. So the plane wavefront will be like this. Now the behavior of the convex lens. Let it is a convex lens, and these are the course of the ray of light. The ray converges at one point in case of convex lens. AB is a incident wavefront and is incident on the lens. Now from figure it is clear that the rays coming from this point and this point covers more distance as it travels through the minimum thickness of the prism, and the ray which passes through the middle covers less distance as the speed of the light in lens decreases. So in the same time this ray reaches up to this point and the rays from this point reaches to this point, covering more distance. So the emerging shape of the emerging wavefront is of this type. Now the behavior of the concave lens. The concave lens behaves as a diverging lens. It is the course of the ray of the light. Why it behaves like this? This is a plane wavefront. The rays coming from these 2 points passes through the maximum thickness of the lens. So it covers less distance, and in the same time the ray which passes through the midpoint cover more distance. So the shape of the emerging wavefront is of this type. Behavior of the convex mirror. It is a convex mirror and it diverges the ray of light. As the wavefront is incident on it, the ray from the midpoint of the mirror is reflected at the same time, while the rays at these points first reaches to the mirror and then reflected. So this ray cover more distance in comparison to the rays coming out from this point. And so the shape of the emerging wavefront is of this type. Now, the concave mirror acts as a converging mirror because in this case, the rays which hit the mirror at this point reflected back immediately, while the ray at the center first goes to the mirror and then reflected. So this ray covers less distance in comparison to this distance. So the shape will be like this, or the emerging wavefront is of this type. Now the effect on the frequency, velocity and the wavelength of the light due to the reflection and the refraction. When the light wave is reflected from the surface, there is no change in frequency, velocity and wavelength, but the phase changes by the 180 degree. Means crest turns into a trough and the trough into a crest. So in case of reflection, no change in frequency, velocity and wavelength. Only there is a phase reversal of pi by 2. In case of refraction, there is no change in frequency, but velocity and wavelength changes. So there is no change in frequency in case of reflection and refraction. In case of refraction, the velocity and the wavelength changes. Let us do a question to make this point clear. A monochromatic light of wavelength 589 nanometer is incident from air on a water surface. Find out the wavelength, frequency and speed of the refracted and reflected light. First we find out for the reflected light and its frequency, velocity and light. Wavelength is same as in the air. So the wavelength in case of reflection same 589 nanometer. Velocity 3 into 10 to the power 8 meter per second. Now the frequency, use the formula C equals to n lambda and it gives you the frequency. It means frequency equals to C upon lambda, that is 3 into 10 to the power 8 upon 589 nanometer. That is 10 to the power, because it is a nanometer. So it becomes 5.09 into 10 to the power 14 Hertz. The frequency is same in the reflection as well as in the refraction. So in case of refraction, frequency remains same 5.09 into 10 to the power 14 Hertz. Now to find out the wavelength and the velocity, use the relation mu equals to C upon V and mu is equal to wavelength in air to the wavelength in medium. And using this relation, you can find out the wavelength and the velocity. Then the coherent sources. Coherent sources are those sources of light which emit light waves of same wavelength, same frequency and in same phase, having the constant phase difference. Such type of the sources of light are called coherent sources. The two independent sources of light, such as two sodium lamps, they cannot be act as a coherent sources because the light from a source is emitted by the matter in bulk. It is emitted by the billions of the excited atoms as the independent sources. So the light wave emitted by the ordinary source undergoes abrupt phase changes. Or we can say when the light is coming out from the two independent sources, then the phase difference between the waves is not constant. Or you can say they don't have the constant phase difference. Coherent sources can be produced by two methods. One is by division of the wavefront, which we have studied, which we will study in Young's double slit experiment, and by the division of amplitude. That is in the case of the partial reflection and the refraction. Thank you.